last topic in this section is reliability importance. If you recall back from section 2.1, the structural importance of component I in a coherent system of n components is denoted by I sub phi of I, and it is a normalizing constant times a summation across vectors of this particular quantity right here. The structural importance only pays attention to the position of a particular component in the system. So it takes care of component I, and that is for I equals 1 to n. So you have n of these structural importances. Because it only pays attention to the position of the component in the system, if you have a series system where each of the components plays a symmetric role, in that case, each of those components will have the same structural importance. Likewise, if you have a parallel system and each of the components in a parallel system play an identical role, in that case, all of the structural importances will be equal. And in fact, it's the case that for a k out of n system, you will have identical structural importance. In this section, we cover the reliability importance. Now, the reliability importance takes two things into account. First of all, it takes into account the position of a component in the system. But the second thing it takes into account is the reliability of a particular component. So the reliability importance of component I in a coherent system of n components is denoted by I sub r of I, and it is the partial derivative of the reliability function with respect to p sub I, and that is for I equals 1 to n. The reliability importance measures the incremental change in the system reliability for an incremental change in the reliability of the ith component. And this is a huge piece of information for a design engineer, because they can look and say, if I can tweak upwards, of course, the reliability of component I by a little bit, then this tells you how much of an impact that will have on the system reliability. So the greatest impact will be the component with the highest reliability importance. There are a couple other alternatives to deriving I sub r of I. Here is one. This starts out with the structure function, and it is x sub I multiplied by the structure function with a 1 in the ith position, multiplied by 1 minus x sub I times the structure function with a 0 in the ith position. When you replace lowercase x with capital X, because now we have random variables, and you take the expected value of both sides of this, you have the expected value of phi of x is the expected value of xi phi of 1ix plus the expected value of 1 minus xi phi of 0ix. By technique number 2 for finding the system reliability, this quantity on the left is the reliability function, and x sub I can be pulled out of this expected value. The expected value of x sub I is p sub I. The expected value of 1 minus x sub I is 1 minus p sub I. And then you have the expected value of phi of 1ix, and we denote that by r of 1ip, and the other is denoted by r of 0ip. You will recognize this as the formula for the decomposition technique. So we did not have to go through that entire derivation. This is nothing more than the decomposition technique. And that's the fifth of the techniques for finding the reliability function. Well, when you differentiate this quantity right here with respect to p sub I, when you take that partial derivative, you get the reliability importance here, when you differentiate this quantity with respect to p sub I, you just get r of 1ip. And when you differentiate this quantity right here, notice the 1 drops out, the 1 times r of 0ip, that drops out, and you're just left with minus r of 0ip. And this is given a number. This is the second technique for finding the reliability importance. The first technique was to just take the partial derivative from the previous slide. And finally, a third technique, if you simply use the expectation technique for finding the system reliability, you wind up with this third way of calculating the reliability importance. Few comments on reliability importance. As mentioned earlier, reliability importance combines the position, which is taken from structural importance, but also uses the component reliability. So it has two things going on. Number two, if you are a design engineer, you want to place your research and development efforts into the component with the highest reliability importance. That's where you will get the most benefit in terms of the system reliability. As mentioned earlier, equation 2 can be found by just differentiating the formula for the decomposition technique with respect to p sub I. And then another question that comes up, when is it the case that the reliability importance and the structural importance are the same? It is the same when every other component other than the component you are looking at has a reliability of 1/2, then the two will be the same. So that is seldom the case, but that is the link between the two of them. Another bullet here is if phi is a coherent structure and each reliability lies between 0 and 1 for I equals 1 to n, then the reliability importance lies between 0 and 1 for all of the components, and n is greater than 1. Finally, you want to use the third equation for calculating the reliability importance when the components are associated. Here are 3 quick examples. The first one is a series system, and for a series system, without loss of generality, we are going to assume this ordering of the component reliabilities. So from that point of view, we can think of this component 1 here as the weakest of the components, and weakest is meant there in terms of reliability. And this last component, component n, can be thought of as the strongest of the components. Well, the definition of the reliability importance is right here. It is the partial derivative with respect to p sub I, and that is finding the reliability importance of the ith component. And that is the partial derivative of the reliability function for a series system. And you know that for a series system, that is simply the product of the component reliabilities. Remember, this quantity here in the brackets is P1 times P2 all the way up to P sub n. When you differentiate that with respect to P sub I, you're going to get the product of every P sub j value other than the ith value. Now here is a quick, easy example. If we have 3 components, and rather than putting their component numbers in here, I'm just going to put their reliabilities. And I'm following the assumption here, which says that put the weakest component as the first component and put the strongest component as the last component. If I want to find R sub I of the first component, that is, if I want to find the reliability importance of this first component, what this formula tells me to do is just multiply the reliabilities of the other two components. So 0.8 times 0.9 is 0.72, and that's the reliability importance of the first component. To find the reliability importance of the second component, again, this formula tells me just multiply the reliabilities of the other two components. So to find the reliability of the second component, I just multiply 0.7 times 0.9, and I get 0.63. Finally, to find the reliability importance of the third component, I simply multiply the reliabilities of the first two components, components 1 and 2, and that gives you 0.56. So notice in this particular example and in general, it is the weakest component, and that is component 1, that has the greatest reliability importance. This is another form of a chain is only as strong as its weakest link. So the weakest link in this case is our first component at 0.7. It has the highest reliability importance, which means that if I can bring that 0.7 up just by a tiny bit, may even make it 0.71, if it gets a little bit bigger, that's going to have the greatest impact on my system reliability. To the design engineer here is you attain the greatest change in system reliability by improving the least reliable component. And that is the reliability importance for a series system. So now what we do is we go to the opposite extreme and we look at the reliability importance of a parallel system. Now once again, without loss of generality, we are going to assume that we have the weakest component as our first component, and we have the strongest component as the last component, component n. So in this case, the reliability importance is, using the definition, partial derivative with respect to p sub I of the reliability function, and the reliability function for a parallel system is 1 minus the product of 1 minus p sub j for j equals 1 to n. When you take the partial derivative of 1, well, 1 is a constant, so that goes away. You have a negative out front, so we'll carry that along. And what this product here is that's 1 minus P1 times 1 minus P2 times 1 minus P3, all the way up to 1 minus Pn. So when you take the derivative of that, all you have to do is take the product of all of the terms that do not involve the ith component. And then, of course, you're going to have a negative 1, which cancels with the negative out front, and that is how you get the reliability importance of a parallel system. Let's do a small example of this one as well. We're going to use those same component reliabilities for a 3-component parallel system. And instead of calling these components 1, 2, and 3, I'm going to put in the reliabilities, and we'll stick with those same numbers, 0.7, 0.8, and 0.9. So the first question is, what is the reliability importance of component 1? The formula right here says take the product of 1 minus P2, so that's 1 minus 0.8, and 1 minus P3, so that's 1 minus 0.9. 0.02 times 0.01 turns out to be 0.02. So that's the reliability importance of component 1. Reliability importance of component 2. Now in this case, when we go to the formula again, what we do is we take 1 minus P1 times 1 minus P3. 1 minus P1 is 1 minus 0.7 or 0.3, and that 0.3 gets multiplied by 1 minus 0.1. I'm sorry, 1 minus 0.9, so 0.3 times 0.1 is 0.03. And finally, the reliability importance of component 3. You go to the formula here. The formula tells you that you take 1 minus P1 times 1 minus P2. 1 minus 0.7 times 1 minus 0.8 gives you 0.3 times 0.2, and 0.3 times 0.2 is 0.06. So now, what is the highest reliability importance? It is the strongest component. So if a design engineer wants to increase the reliability of this system, that design engineer should put their focus onto the strongest component, which is this third component. So that's down here in the conclusions. The strongest component, which is component N, has the greatest reliability importance, and a design engineer can attain the greatest change in system reliability by improving that most reliable component. The last example here is to find the reliability importance of the third component using two different methods, equation 1 and equation 2. So we start out by writing the reliability function R of P. Now notice that that P with the line underneath it in this particular setting means P1, P2, P3 as arguments. Well, we start out, we have component 1 in series with this subsystem, so we have a P1, and we are multiplying that P1 by the reliability function for the parallel system consisting of components 2 and 3, and by now that should be familiar. 1 minus P2, 1 minus P3. And again, those two are multiplied because those two are in series. That is, component 1 is in series with the parallel subsystem consisting of 2 and 3. Well, if you multiply inside the brackets, you multiply that quantity out, you will see there's going to be a 1 minus 1, which will go away. So you are left with just P2 plus P3 minus P2, P3. When that all gets multiplied by P1, you get P1, P2 plus P1, P3 minus P1, P2, P3, and there it is written out. Now, to use equation 1, I'll write that here. Using equation 1, what you are going to get is you're going to get I sub R of 3. Remember, we're finding the reliability of the reliability importance of the third component, and this is going to be the partial derivative of R of P with respect to P3. So all you have to do is take a partial derivative of the quantity above. Notice the first term contains no P3, so the derivative of that is 0. And then you have P1 times P3. Well, P3 here is treated, that's what we're differentiating with respect to, so this is just the constant P1 multiplied by P3, so its partial derivative is P1. And then finally, the derivative with respect to P3 of P1 times P2 times P3, that's just P1 times P2. Finally, we want to use equation 2 when putting this together. And in this case, I sub r of 3 is equal to r of 1 in the third position, p, minus r of 0 in the third position, p. Now we have to think a little bit in terms of what's going on here. So r with a 1 in the third position is the same as taking this system, and by saying there is a 1 right here, we're saying this is perfect, and I'm going to draw a line right there. That's the way you think of putting a 1 in for the third component. And what just happened? Component 2 became irrelevant, didn't it? Doesn't matter what component 2's state is. The only thing that matters now is component 1. So that system now looks like this. Now let's take a look at this second system here, r of 0, 3p. That means you put a 0 in the third position. That's the same as saying this thing isn't even here. Now this system right here now looks like a 2-component parallel system with just components 1 and 2. 2-component series system with components 1 and 2. So finally, the last thing we do is we say, what is the reliability of this system right here? Well, that's P1. And finally, what is the reliability of this system right here? That is P1 and P2. And notice that matches exactly what we got previously using equation number